Let's look at the idea of alternating current. So here we have our DC source. So in DC source, the current, it turns out to be constant for quite some time. Gradually it will reduce, but overall for matter of few minutes or hours, the current will look the same. When it comes to our AC source, what is that we're looking at? We're looking at a time varying value. So the current or the voltage, it keeps varying with time. So basically how can we see this is how you guys can check your function is varying with time and all of that is pick up say two different points, check the amplitude and the direction. So that would be your amplitude, that is how far away it is from the mean value. So you can see that amplitudes are different and we can see that one is positive, another is negative. So even the direction is different. So this is contrast. What is contrast? AC is a contrast to direct current, wherein we have the flow of current in only one direction. While in AC, we have current flowing periodically with reverse direction and change in its magnitude as a function of time. So this is a function of time and the average turns out to be 0. Okay, it's something like this. So here I have a wave. So this wave can vary its frequency in this manner. So we can see that it's not stationary like this. If it's stationary, then we can just use sine function. So let me build it up actually. So we're looking at the math now. So we're figuring out the instantaneous EMF. Say your EMF is equal to some maximum value E0. How will that look like? It look like this. I0, some maximum value. It will look like a straight line. But I know that it has to vary with time. Right? It is sinusoidal. So we can multiply with sine of some theta. So this will give us a sinusoidal wave. But it's not a stationary one. It's not stationary that we can just put value of theta as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's not so. It has to be a function of time. It should vary. So the theta has to vary, but it has to be function of time. So theta has to be equal to some function of time. So how will we make it as function of time? So what is that we're looking at? We're looking at this omega t. So this is your angular velocity. And this is your time. So basically, I end up working with this. We end up working with this actually, not I. So this is how you can represent an AC current. This represents the maximum value it can have, right? Maximum displacement. And this represents the sinusoidal nature, sine nature, while this represents function of time. Does it make sense? If I make this as 1, then you get a sine wave whose amplitude is 1. Basically, okay, this is amplitude is 1. So this is sine wave, your traditional one. Then if I make omega t as say 1, oh, I got it at one go. It would look like this. So, but it's varying with time. We have time varying value. Okay, again, this naming convention is for something else. Position, actually this is for sound topic, but I borrowed it from there, right? Sound also can vary with time. So instantaneous current. So we know that your voltage is varying that way. For a circuit which has, say, a resistor, let me do a quick diagram. So we are looking at instantaneous current. So that's your E naught sine of omega t. That's your resistance and current. So as per Kirchhoff's law, what will you end up with? IR is equal to omega t. Epsilon naught sine omega t. So I will be equal to I naught, that's the maximum value of current, sine omega t. What did I do? I just substituted I naught as epsilon naught by R. Yes, very simple set of expression. So the complexity increases from the next video, if I remember right. So finally, that few terms that we need to know in anything that varies with time, right? So time period, frequency and amplitude. So you guys know all of that. Just a point of revising. So this is a small introduction to AC.